Okay, this video we will show the example of the problem, the beam problem. We will apply the finite element method to solve the beam problem. This problem is the beam subject to the point load at the left end, and on the right end is a fixed support, and at the middle of the beam subject by roller, the support is roller. So according to this, first thing that we have to do, the step of finite element is just starting with the first step that we have to discretize the element. First, that's right now we may discretize the element into, we may select just only two elements for this case. That is the first element. This is for the first element. This is the second element. Okay, and the first node is over here. This is the second node, and this is the third node. Okay, and don't forget that for the beam element, we have to remember that we have to mention about the sign convention first. You have to set up the global coordinate. This is the global coordinate x and y. X is positive in to the right is positive, and y is upward. It's a positive one. This is a global coordinate, and also it's same as the local coordinate. For local coordinate, for this case, it's same. X is to the right, y is upward. Okay, so according to this, the degree of freedom is composed of d1y, okay, d2y, and also for moment, this is phi1, okay, phi2. Okay, according to this, this is compatible with the force, the nodal force. Nodal force is the same direction. It should be F1y, F2y, and for compatible with phi1, that is M1, this M2. Okay, this is the positive sign convention for beam. According to this, we may just review about the element stiffness. What is the element stiffness for beam? That is for the Timoshenko beam. For the Euler-Bernoulli beam. For this case, if we consider that the beam is long enough, and it is we can apply the Euler-Bernoulli beam theory for this case, and we will see that the stiffness K is equal to what for Euler-Bernoulli beam? Element stiffness is equal to EI over L cubed. Okay, and then it's equal to 12, 6L. Okay, the beam length is L, minus 12 and 6L. Okay, and 4L squared minus 6L, 2L squared. Okay, this 12, and this minus 6L. Okay, and 4L squared. For this case, it is symmetry. Okay, now we already know the sign convention and the element stiffness. After that, we form the element. Okay, we form the element stiffness matrix. Is actually it is has the same length for both elements. It has the same length, so it should have the same element stiffness, same length, same property. For this case, it maybe have the same element stiffness. And after that, we assemble it together. Okay, assemble it together. This is for element number 1. That is connected with, for element number 1, element number 2 is connect together at node 2. Okay, so this is phi 2. Okay, according to this, so when we assemble it together, we will obtain, we call it as 3 node, right? As 3 node. Each node has 2 degree of freedom. So the total element stiffness is equal to 6 by 6. Okay, 6 by 6 is for node number 1, this is for node number 2, and this is for node number 3. Okay, and this is the metric is symmetry. Okay, and after that, we obtain the total element stiffness already. Now we have to apply the boundary condition. Okay, this is a governing equation that we obtain for the element stiffness after we substitute the constant value into the element stiff, the global element stiffness, and we simplify the equation. Is we obtain equation number 2, right? And but boundary condition is apply at node number 2 and node number 3. The boundary condition are composed of d2y equal to 0, d3y equal to 0, and phi 3 equal to 0. According to this, if we applying the boundary condition, you see that the column number 2 is maybe cut off. Okay, this is the homogeneous boundary condition, right? We can cut off the column and also the row. Oh, sorry. It's not the second row. It should be the third row. The third row, d2y. Okay, so we cut off the third row and third column. Okay, we eliminate third row and third column. And also for d3y and the phi 3 and phi 3. Okay, so we eliminate the fourth, the fifth and the sixth column and the fifth and the sixth row. Right now, we should obtain the element stiffness after we apply boundary condition like this, and we substitute the applied load. That is, for this case, it has just only node number 1, but the load is downward, right? If the load is downward, if we compare with the sign convention that we set up, it's upward as positive. Okay, upward as positive, just as for local and global. So when we substitute into the equation, P should be negative sign. Okay, and for the moment in at node number 1 and node number 2 are equal to 0, we call this no applied load. And after that, we see that from this equation, it is 3 equation with 3 unknown like this. We can solve for d1y, phi 1 and phi 2 like this. We obtain the solution already. We can solve analytically because it's just only 3 equation and 3 unknown. Okay, after we obtain the solution, right now it is go to the post-processing that we would like to find the reaction force. Okay, so we come back to the total system equation again, and then by 6 by 6 equation, according to 6 by 6 equation, we substitute the solution, the obtained solution that we have from the previous step into the equation and also for the boundary. Okay, right now, after we solve this equation, we can find the nodal force at each node. The nodal force at each node represent the applied force and also the reaction force. For the case of at node number one, we will see that it should be obtained minus P, that is equivalent to the applied load. Okay, and at node number one also the moment, the applied moment is equal to 0. And for node number two, we find that the force is equal to 5/2P. Okay, so it means that, and it's positive. Positive is mean that the force F to Y is upward. Okay, and for M2 is equal to 0 because we have no applied load on that node. Okay, and also for node number three, that is the fixed end, we have the reaction force and also the moment. The reaction force is negative. It means that it should be downward. Okay, it should be downward. So according to this, when we check the summation of force, we found that it is in equilibrium. That is mean that in summation F is equal to 0. And also for moment, moment at node number 3 is positive, that is a half PL. What does positive mean? It means that the moment, the direction of moment should be counterclockwise according to the node convention. Don't confuse with the beam convention. The solution obtained from the finite element is a node convention. It follows the sign convention that we defined before. Okay, so at node number 2, the moment is counterclockwise as a positive. Okay, right now we already have the reaction force, and then if we would like to find the internal force is mean that the shear force and bending moment. Okay, we will consider each element. Come back to consider the equation for each element. As we may starting with the element number 1 first. For the first element, the element equation can be written like this. We substitute the displacement, the degree of freedom that we already obtained into this equation, and we can solve for F1y, M1, F2y, and M2. Okay, according to this, we found that F1y equal to minus P, right? That is equivalent to the applied load. M1 equal to 0. F2y equal to P. M2 equal to minus PL. Okay, and then according to this, we can use the solution that we obtained over here. We can draw the free body diagram. This is for node number 1, for element number 1. The process for element number 2 is the same like this. Okay, and after we have the solution for both elements, that is element number 1, element number 2, we can draw the free body diagram. You use the solution at node, draw the free body diagram like this, and we can draw the shear force and bending moment diagram also. According to the nodal force that we obtain for each element, if we use the solution that we obtain and plot it and a shear force diagram and bending moment diagram, we obtain the solution like this. And you have to mention that the solution that we obtain is just only at node. And for this case, when we connect the value at node together, we will obtain the shear force diagram and also for the bending moment diagram, because the The solution that we obtain is just for the general basic case, that is the beam is subject just only for the concentrate load. Okay, so the shear force and bending moment diagram is just the linear shape, and for shear it's just a linear and continuous in the range of each element. But for the bending moment, it's just in the linear form like this. You may compare the solution by analytical solution also, and you see that it is identical to the analytical solution. Okay, so we were talking about the more detail in the beam problem again when we consider in another example that is maybe include the load inside of the beam or the distributed load. Okay, that we may mention to that again. Okay, that's this all for this clip video.